at n. So let's look at n now. What does n do when it hits the bottom state? Well, it is by definition A plus A minus on O, but we already know that A minus on O gives 0, so this is 0. It's an eigenvector of n with 0 eigenvalue. So there must be an the bottom state has to have 0 value of n. That's an abstract argument, but yeah.
So if 0 is an eigenvector, then should there be an eigenvector of 0 on the far right-hand side?
Wait. This 0 here, this state, and this are two different things. That's the eigenvector, and it's normalized to 1. And it's not 0 in any sense. It's just that its name is 0. You know, if I called my friend Art here 0, that wouldn't mean Art wasn't here or didn't exist. It would just mean, being unpleasant. I'm calling him 0. Yeah, you can write 0 as a ket, but you have to understand it's not this 0. This is 0.
0 times that answers your question.
0 times anything is 0, so you can write.
It's a vector on the left-hand and right-hand side, so you can put the vector in there, and it's just a 0 vector. Thank you.
Yeah, but you must not call it this vector. Whatever name you give it, you've got to give it some. And the tradition is just not to write it as a vector, but just to call it 0. In the abstract theory of vector spaces, you introduce a vector called 0, and it's sort of special. It's the only one that doesn't have a ket sign. But as you say, it is just another vector, a rather special one. Yeah. Okay. All right. So the bottom of the tower, the bottom of the energy spectrum has to be energy h bar omega times 1/2, with n equal to 0, big N equal to 0, also a little n. But let's see if we can see how far we can go in calculating all of the wave functions. Can we calculate the wave functions themselves? Now, you might ask, I can write a Schrodinger equation. I just use for P in the top equation, I use for T, d by dx. For a time-independent Schrodinger equation, the right-hand side is just the energy eigenvalue times psi. Question, is it really true that you can only solve that equation? In fact, we could write down the equation. Let's write down the equation. Just time-independent, here it is, time-independent Schrodinger equation. It's minus d by dx squared, or ordinary derivative, minus 1/2. The 1/2 is the half in front of the Hamiltonian there. P squared is d second by dx squared, psi of x, plus the potential energy, plus omega squared x squared times psi of x. And if this is the time-independent Schrodinger equation, then what I want to do is to solve the equation that this is equal to, let's call it E for the eigenvalue for energy, times psi of x. That's the same as writing P squared plus omega squared x squared on a vector is equal to E times that vector. Okay, now, if you know anything about differential equations, you'll know this is a second-order differential equation. You can always solve it for any value of the energy here. But what will happen for most values of the energy is the wave function will not go to 0 at infinity. Even worse, it will exponentially explode and get big. It won't be normalizable. It will not have a finite probability under it. There's no way to normalize it. If you try to normalize it, it'll just be 0 because the integral under the square of the wave function will be infinite. To get rid of that infinity, you'll have to divide by it, and the wave function will just be 0 everywhere. So the rule is, one more rule, and we've talked about this last quarter or 3 quarters ago or whenever it was, is that what you mean by an honest vector here is one whose square integral, the square of, which is square integrable. Integral psi star psi equals 1. Okay. There are some exceptions to this. For a particle moving on an infinite line, sometimes we introduce momentum states and position states, which are a little weird in this way. But we would like total probability to be finite, certainly not exponentially exploding. So this is one additional restriction, and it's when the wave functions are restricted in this manner, when they really form an honest and good vector space, then that's when the rest of this applies here. It only applies if we're interested in the square integrable wave functions, which we are. And so the point is that when we write down the Schrodinger equation, there are certain definite values of energy which will have square integrable wave functions. Those are the true honest eigenfunctions. If the wave function blows up and goes to infinity, we just throw them away, because they're not in space. Okay, let's see if we can find psi naught, the ground state wave function. We could write the original Schrodinger equation for it, but we can be smarter than that. Instead of writing h on psi equals e psi, let's write a smarter equation, a simpler equation. Let's use the fact that we know that the annihilation operator, the lowering operator on the ground state, we don't need to call it psi naught, gives 0. Okay, what is A minus? A minus, just want to get my signs right. A minus is proportional to P minus I omega x. Now, there's some factors in the denominator there, but we don't care about them because we're just going to write that this times psi of x equals 0. And numerical factors like square roots of omega, they don't matter in this equation. Just multiply through by them. And now, remember what P is. P is minus I d by dx. Minus I d by dx minus I omega x times psi of x equals 0. Now we have a much simpler equation than we had before. It doesn't even have any second derivatives in it. It only has first derivatives in it. So we can try to solve it. The trick for solving an equation of motion like this, anybody know what the trick is? There's only a finite number of tricks in solving differential equations. There's a handful of tricks. What's that? No, there's only one variable. What are you going to separate? That's it. Right. Okay. One very standard trick for linear equations like this is to write the wave function as the exponential of something else. Now, this is just a matter of experience. I can't tell you how to guess that.
Yeah, you can guess it because when you multiply through by dx, you get x dx. So the equation comes out as a derivative over